Stars are massive, self-luminous spheres of plasma held together by gravity and powered by nuclear fusion in their cores. They are the fundamental building blocks of galaxies and among the most important objects in astrophysics. A star forms when gravity causes gas, primarily hydrogen with some helium, to collapse until pressure and temperature at the center become high enough to ignite fusion. Once fusion begins, the outward pressure from energy production balances the inward pull of gravity, creating a stable object that can persist for millions to trillions of years, depending on its mass. The scale of stars varies enormously. Their masses range from about 0.08 times the mass of the Sun, the minimum required to sustain hydrogen fusion, to more than 100 times the Sun's mass in rare, extremely luminous stars. Their diameters can be smaller than Earth in the case of compact remnants, or large enough to engulf the orbit of Mars for supergiant stars. Despite this diversity, all true stars share the defining property of sustained nuclear fusion at some point in their existence. Stars are composed of plasma, meaning their atoms are ionized into nuclei and free electrons due to extreme temperatures. Core temperatures typically reach millions of Kelvin, while surface temperatures range from about 2000 K for cool red stars to over 40,000 K for the hottest blue stars. These temperatures determine the color and spectral characteristics of a star. Cooler stars emit more red and infrared light, while hotter stars emit more blue and ultraviolet radiation. Energy production in stars occurs through nuclear fusion, primarily by converting hydrogen into helium. In lower mass stars, fusion proceeds mainly through the proton-proton chain reaction, while in more massive stars the carbon-nitrogen-oxygen (CNO) cycle dominates. Fusion converts a small amount of mass into energy, according to Einstein's mass-energy equivalence, and this energy travels outward from the core before being radiated into space as starlight. Stars are not isolated phenomena. They strongly influence their surroundings. Their radiation heats nearby gas and dust. Their stellar winds shape interstellar environments, and their deaths can dramatically alter galaxies. Massive stars end their lives in supernova explosions that eject heavy elements into space, enriching the interstellar medium with the raw materials needed to form planets, moons, and eventually life. Even smaller stars contribute to galactic evolution through gradual mass loss and radiation. From a cosmic perspective, stars are essential markers of time and structure. Because their properties depend on mass and composition, astronomers can use stars to determine the age of star clusters, the history of galaxies, and the expansion rate of the universe. Starlight also carries information across vast distances, allowing observation of objects billions of light years away, and providing a record of conditions in the early universe. Stars matter because they are the primary engines that convert simple elements into complex ones and transform gravitational energy into light. Every atom heavier than helium found on Earth was created inside a star or during a stellar explosion. Without stars, there would be no galaxies as we know them, no planetary systems, and no chemical complexity sufficient for life. Stars form from the gravitational collapse of dense regions within large clouds of gas, and thus known as molecular clouds. These clouds are primarily composed of hydrogen molecules, with helium and trace amounts of heavier elements. They exist in a cold state, typically at temperatures of 1030 Kelvin, which allows gravity to overcome thermal pressure when sufficient mass accumulates in a localized region. Star formation begins when an external trigger, such as a shock wave from a nearby supernova or the collision of molecular clouds, compresses part of the cloud and initiates collapse. As collapse starts, the dense region fragments into smaller clumps, each of which can become an individual star or a multiple star system. Gravity pulls material inward, causing the clump to contract and heat up. During this phase, the object is called a protostar. The protostar continues to accrete mass from its surrounding envelope, and its central temperature and pressure steadily increase. At this stage, energy is produced mainly by gravitational contraction rather than nuclear fusion. Angular momentum plays a critical role during star formation. As the collapsing cloud contracts, it spins faster, leading to the formation of a rotating accretion disk around the protostar. Material in this disk gradually spirals inward and feeds the growing star. At the same time, strong magnetic fields and rotation drive bipolar jets that eject some material away from the system. These jets remove excess angular momentum, allowing further collapse and growth of the protostar. The duration of the protostellar phase depends on mass. Low-mass stars may take tens of millions of years to reach full stability, while high-mass stars form much more rapidly, sometimes in less than a million years. As mass increases, the core temperature eventually rises above approximately 10 million Kelvin. At this point, hydrogen nuclei begin to fuse into helium, releasing energy. When the outward pressure from fusion balances gravitational contraction, the star enters a stable phase of its life. Once nuclear fusion becomes the dominant energy source, the object is considered a true star and is said to have reached the main sequence. The mass accumulated during formation largely determines the star's entire future. Higher mass stars burn fuel more rapidly and live shorter lives, while lower mass stars burn fuel slowly and can remain stable for billions or even trillions of years. The chemical composition of the original cloud also influences stellar properties, particularly luminosity and temperature. Star formation is an inefficient process. Only a small fraction of the gas in a molecular cloud ends up in stars, while the rest is dispersed back into interstellar space by radiation pressure, stellar winds, and jets from newly formed stars. This feedback regulates further star formation and prevents all available gas from collapsing at once. As a result, star formation occurs in episodes and clusters rather than uniformly throughout galaxies. The birth of stars is an ongoing process throughout the universe. In spiral galaxies, star formation is most active in the dense spiral arms, while in irregular galaxies it can occur in widespread bursts. In contrast, elliptical galaxies show little or no current star formation because their gas reservoirs have largely been exhausted or expelled. The continuous cycle of cloud collapse, star birth, and feedback is a key mechanism driving the long-term evolution of galaxies. Stellar nurseries are regions within molecular clouds where physical conditions allow large numbers of stars to form in relatively short astronomical timescales. These regions are characterized by high gas density, low temperature, and significant amounts of dust that shield the interior from external radiation. Molecular hydrogen dominates their composition, but because it is difficult to detect directly, these regions are commonly traced using molecules such as carbon monoxide. The presence of dust causes stellar nurseries to appear dark at visible wavelengths, while glowing strongly in infrared and radio observations. The structure of stellar nurseries is highly irregular and turbulent. Supersonic motions within the gas create filaments, clumps, and dense cores. Star formation occurs primarily in the densest cores, where gravity overcomes internal pressure. Observations show that stars tend to form in groups rather than isolation, leading to star clusters and associations. This clustered formation reflects the fragmentation of the parent molecular cloud and the shared conditions under which stars are born. Temperature regulation is crucial in stellar nurseries. Efficient cooling mechanisms, mainly through molecular line emission and dust radiation, allow gas to remain cold enough to collapse. If the gas were significantly warmer, thermal pressure would prevent star formation. Dust grains play a dual role by aiding cooling and providing surfaces on which molecules can form, further enhancing the chemical complexity of these regions. Massive stars have a profound impact on their birth environments. Once they begin emitting intense ultraviolet radiation, they ionize surrounding hydrogen, creating HII regions of hot This radiation and the associated stellar winds can compress nearby gas, potentially triggering new star formation, or they can disperse the cloud and halt further collapse. This dual effect, known as feedback, strongly influences how many stars ultimately form in a given nursery. Stellar nurseries are observable across the Milky Way and other galaxies. In the Milky Way, they are concentrated along the galactic disk, particularly in spiral arms where gas density is highest. In starburst galaxies, stellar nurseries can be extraordinarily active, producing stars at rates hundreds of times greater than that of the Milky Way. These environments often host very massive stars that form quickly and evolve rapidly. The initial mass function, which describes the distribution of stellar masses at birth, is shaped within stellar nurseries. Observations indicate that low-mass stars are far more common than high-mass stars, regardless of environment. This consistency suggests that the physical processes governing fragmentation and collapse are broadly universal, although extreme conditions can slightly alter the relative numbers of massive stars. Stellar nurseries are transient on cosmic timescales, over periods of a few million to tens of millions of years. Radiation, winds, and supernova explosions from newly formed stars disperse the remaining gas. Once the gas is removed, star formation ceases, leaving behind clusters of stars that gradually drift apart under gravitational interactions. The study of stellar nurseries therefore provides direct insight into the earliest stages of stellar evolution and the mechanisms that regulate star formation across the universe. Stars are classified primarily by their mass, temperature, luminosity, and evolutionary stage. The most widely used system is the spectral classification scheme, which groups stars according to surface temperature and the characteristics of their absorption lines. This sequence, ordered from hottest to coolest, is O, B, A, F, G, K, and M. Each class is subdivided numerically from 0 to 9 to provide finer temperature distinctions. This classification reflects fundamental physical differences rather than superficial appearance. Mass is the most important property determining a star's behavior and lifespan. Low-mass stars, with masses less than about half that of the Sun, burn their fuel slowly and can remain stable for extremely long periods. Intermediate-mass stars, similar to the Sun, have moderate lifespans and predictable evolutionary paths. High-mass stars consume their nuclear fuel rapidly, shine intensely, and live comparatively short lives. Differences in mass influence core temperature, fusion processes, luminosity, and ultimate fate. Temperature-based classification correlates strongly with color and luminosity. O-type stars are extremely hot, often exceeding 30,000 Kelvin, and emit large amounts of ultraviolet radiation. They are rare but dominate the energy output of young star-forming regions. B and A-type stars are also hot and luminous, while F and G-type stars include many stable, long-lived stars. K and M-type stars are cooler, dimmer, and far more numerous, with M-type red dwarfs making up the majority of stars in galaxies. Stars are also classified by size and luminosity, using the Hertzsprung-Russell diagram, which plots luminosity against temperature. Main-sequence stars occupy a continuous band, where they spend most of their lives fusing hydrogen in their cores. Giants and supergiants appear above the main sequence due to their high luminosity and large radii, despite often having cooler surfaces. White dwarfs lie below the main sequence, characterized by high temperature but low luminosity due to their small size. Red dwarfs form a distinct and important category. These low-mass, cool stars are fully convective, meaning energy is transported throughout the entire star rather than in layers. This allows them to use a larger fraction of their hydrogen fuel and gives them lifespans far exceeding the current age of the universe. Despite their abundance, their low brightness makes them difficult to observe at great distances. Giant and supergiant stars represent advanced evolutionary stages rather than separate birth categories. Giants are stars that have exhausted hydrogen in their cores and expanded as fusion shifts to surrounding shells. Supergiants are extremely massive stars in late evolutionary phases, with radii hundreds to over 1,000 times that of the Sun. These stars lose mass rapidly and often end their lives in supernova explosions. Compact stars form another major classification group. White dwarfs are the dense remnants of low and intermediate mass stars, composed mainly of electron-degenerate matter. Neutron stars result from the collapse of massive stellar cores and are composed almost entirely of neutrons, with densities comparable to atomic nuclei. Although black holes are not stars in the active sense, they originate from stellar evolution and are often grouped with stellar remnants. These classification systems are interconnected. A star's spectral type, position on the Hertzsprung-Russell diagram, and evolutionary category all reflect the same underlying physical properties. By classifying stars, astronomers can infer their age, composition, internal structure, and future development, making stellar classification a foundational tool in understanding the universe. The main sequence is the dominant phase in the life of a star, during which it steadily fuses hydrogen into helium in its core. This phase begins once a star achieves hydrostatic equilibrium, where the outward pressure generated by nuclear fusion balances the inward pull of gravity. On the Hertzsprung-Russell diagram, main sequence stars form a continuous diagonal band extending from hot, luminous stars to cool, dim ones. The position of a star along this band is determined primarily by its mass. Mass controls the internal conditions of a main sequence star. Higher mass stars have greater core pressures and temperatures, which cause nuclear fusion to proceed at a much faster rate. As a result, these stars are far more luminous but consume their hydrogen fuel rapidly. Lower mass stars have cooler cores and slower fusion rates, producing much less energy but sustaining fusion for vastly longer periods. This relationship explains why bright blue stars are short-lived, while faint red stars persist for extremely long times. Energy generation on the main sequence depends on stellar mass. In stars with masses similar to or lower than the Sun, hydrogen fusion occurs mainly through the proton-proton chain reaction. In more massive stars, the carbon-nitrogen-oxygen cycle dominates, using heavier elements as catalysts to accelerate fusion. Although the underlying nuclear reactions differ, the net result in all main sequence stars is the conversion of hydrogen into helium with the release of energy. The length of time a star remains on the main sequence varies widely. Massive stars may spend only a few million years in this phase, while Sun-like stars remain on the main sequence for roughly 10 billion years. The smallest red dwarf stars can remain in the main sequence phase for trillions of years, far exceeding the current age of the universe. No star more massive than about 8 times the Sun's mass will ever experience such longevity. Main sequence stars exhibit relatively stable physical conditions compared to other stages of stellar evolution. Their luminosity and size change slowly over time as helium accumulates in the core and hydrogen becomes depleted. As the core composition changes, the star gradually becomes more luminous and slightly larger, even while remaining on the main sequence. This slow evolution provides a predictable framework for estimating stellar ages. The main sequence plays a central role in astronomy because it allows stellar properties to be inferred from observable quantities. By measuring a star's luminosity and temperature and locating it on the Hertzsprung-Russell diagram, astronomers can estimate its mass, age, and evolutionary status. This method is particularly powerful for studying star clusters, where stars formed at roughly the same time but have different masses. Eventually, a main sequence star exhausts the hydrogen fuel in its core. When this occurs, fusion can no longer counteract gravity at the center, and the core begins to contract. This marks the end of the main sequence phase and the beginning of a new stage of stellar evolution, which depends strongly on the star's mass. Despite this eventual transition, the main sequence remains the longest and most stable period in a star's life, encompassing the majority of stellar existence in the universe. Red dwarfs are low-mass, low-luminosity stars that belong primarily to the M spectral class, and at the high-mass end, to the cooler K class. They have masses ranging from about 0.08 to 0.6 times the mass of the Sun, with the lower limit representing the minimum mass required to sustain hydrogen fusion. Below this threshold lie brown dwarfs, which do not qualify as true stars. Red dwarfs have surface temperatures typically between 2300 and 3800 Kelvin, giving them a reddish appearance when observed. These stars are by far the most common type in the universe. In the Milky Way, red dwarfs account for roughly 70 to 80% of all stars by number. Their low luminosity makes them difficult to detect at large distances, which is why they were historically underrepresented in early stellar catalogs. Despite their abundance, their combined light contributes only a small fraction of the total brightness of a galaxy. The internal structure of red dwarfs differs significantly from that of more massive stars. Most red dwarfs are fully convective, meaning that energy generated in the core is transported throughout the entire star by convective motion, rather than by radiation in layered zones. This complete mixing prevents the buildup of an inert helium core and allows the star to utilize nearly all of its hydrogen fuel over time. Hydrogen fusion in red dwarfs occurs through the proton-proton chain reaction, but at a much slower rate than in more massive stars. The low fusion rate results in very low energy output and extremely long lifespans. Many red dwarfs are expected to remain on the main sequence for hundreds of billions to trillions of years, far longer than the current age of the universe. As a result, none of the oldest red dwarfs have yet exhausted their hydrogen fuel. Red dwarfs are often magnetically active, especially in their youth. Strong magnetic fields can produce star spots, flares, and bursts of radiation across the electromagnetic spectrum. Some red dwarfs exhibit powerful flares that can temporarily increase their brightness by large factors. This activity is linked to rapid rotation and deep convection, both of which enhance magnetic dynamo processes. Planetary systems are common around red dwarfs. Because these stars are cool and dim, their habitable zones lie very close to the star. Planets in such orbits are more likely to be tidally locked, with one side facing the star permanently. While the proximity makes planets easier to detect, stellar flares and high-energy radiation can pose challenges to atmospheric stability and potential habitability. Over cosmic timescales, red dwarfs evolve very slowly. As they gradually convert hydrogen into helium, they become slightly hotter and more luminous, rather than expanding into red giants like sun-like stars. Current theoretical models predict that red dwarfs will eventually become hotter, bluer stars, before finally exhausting their fuel and ending as helium-rich remnants. However, the universe is not yet old enough for any red dwarf to have reached its final evolutionary stage. Red dwarfs play a crucial role in galactic structure and evolution due to their sheer numbers and longevity. They dominate the stellar mass budget of galaxies and serve as long-term repositories of baryonic matter. Their persistence ensures that star formation and stellar light will continue in the universe for an extraordinarily long time after more massive stars have completed their life cycles. Giant and supergiant stars are highly luminous, large radius stars that represent advanced evolutionary stages of stellar life, rather than distinct formation types. Giants typically evolve from low to intermediate mass stars after they exhaust hydrogen in their cores, while supergiants arise from very massive stars. Their defining characteristic is their expanded outer envelope, which increases luminosity dramatically even when surface temperatures are relatively low. Red giants form when a star similar in mass to the Sun depletes core hydrogen. The core contracts under gravity and heats up, while hydrogen fusion continues in a surrounding the core. Energy from this shell causes the outer layers to expand and cool, increasing the star's radius by tens to hundreds of times. Despite cooler surfaces, red giants are far brighter than main sequence stars due to their enormous surface area. Supergiants originate from stars with initial masses typically greater than about 8 times that of the Sun. These stars evolve rapidly due to high fusion rates. After leaving the main sequence, they expand into red supergiants or, in some cases, remain hot as blue supergiants depending on mass, composition, and internal mixing. Supergiants can have radii hundreds to over 1,000 times that of the Sun and luminosities, tens of thousands to millions of times greater. The internal structure of giants and supergiants is layered and complex. Fusion occurs in shells around an inert or actively fusing core. In massive supergiants, multiple fusion shells may exist simultaneously, producing heavier elements in sequence. These stars can fuse elements up to iron in their cores, a process that occurs over progressively shorter timescales as heavier fuels are consumed. Mass loss is a major feature of giant and supergiant stars. Their low surface gravity allows stellar winds to remove large amounts of material over time. Red supergiants, in particular, lose mass at very high rates, enriching the surrounding interstellar medium with gas and dust. This expelled material contributes to future star and planet formation and can create observable nebulae around the star. The lifetimes of giant and supergiant phases are short compared to the main sequence stage. A sun-like star may spend billions of years on the main sequence, but only a few 100 million years as a red giant. Supergiant phases in massive stars may last only a few million years or less. Despite their brief existence, their extreme brightness makes them visible across vast cosmic distances. The final fate of giant and supergiant stars depends strongly on mass. Low and intermediate mass giants eventually shed their outer layers, leaving behind dense cores that become white dwarfs. Massive supergiants undergo core collapse once iron accumulates, triggering supernova explosions. These explosions disperse newly formed heavy elements into space and often leave behind neutron stars or black holes. Giant and supergiant stars are crucial to cosmic evolution. They dominate the visible light of young and intermediate-age stellar populations and play a central role in chemical enrichment. Their expansion, mass loss, and eventual destruction redistribute matter and energy throughout galaxies, shaping the environments in which subsequent generations of stars and planetary systems form. White dwarfs are compact stellar remnants formed from the cores of low and intermediate mass stars after they have exhausted their nuclear fuel. When such a star reaches the end of its red giant phase, it expels its outer layers into space, leaving behind a dense core that no longer undergoes fusion. This remnant is a white dwarf, supported against gravitational collapse by electron degeneracy pressure rather than thermal energy from fusion reactions. The mass of a white dwarf is comparable to that of the Sun, but its size is similar to that of Earth. This extreme compression results in very high densities, often exceeding 1 million grams per cubic centimeter. In this state, electrons are forced into close proximity, and quantum mechanical effects provide the pressure needed to counter gravity. The more massive the white dwarf, the smaller its radius, a counterintuitive property unique to degenerate matter. White dwarfs are composed primarily of carbon and oxygen, which are the fusion products of helium burning in the progenitor star. Less massive progenitors may produce helium white dwarfs, while the most massive stars that still avoid supernova explosions can leave behind oxygen neon white dwarfs. The exact composition depends on the initial mass and evolutionary history of the original star. At the time of formation, white dwarfs are extremely hot, with surface temperatures exceeding 100,000 Kelvin. However, they have no internal energy source and shine only by radiating their stored thermal energy into space. Over billions of years, they gradually cool and fade, This predictable cooling process allows astronomers to use white dwarfs as cosmic clocks to estimate the ages of stellar populations and the Milky Way itself. White dwarfs follow a well-defined mass limit known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. Above this limit, electron degeneracy pressure can no longer support the star against gravity. Isolated white dwarfs cannot exceed this limit, but in binary systems, mass transfer from a companion star can push a white dwarf toward instability. In close binary systems, white dwarfs can produce dramatic phenomena. If a white dwarf accretes material from a companion, hydrogen can accumulate on its surface and ignite in a thermonuclear runaway, producing a nova. If the white dwarf grows close to the Chandrasekhar limit, the entire star may undergo a catastrophic thermonuclear explosion known as a Type Ia supernova, completely destroying the white dwarf and releasing vast amounts of energy. White dwarfs are common in the universe because the majority of stars are not massive enough to end their lives as supernovae. In the Milky Way, white dwarfs represent the final evolutionary state of most stars that have completed their life cycles so far. Their abundance provides key information about past star formation rates and stellar evolution. Over extremely long timescales, white dwarfs are expected to cool to the point where they emit little detectable radiation. These hypothetical objects, sometimes referred to as black dwarfs, have not yet formed because the universe is not old enough. The study of white dwarfs, therefore, not only reveals the fate of most stars, but also provides insight into the long-term thermal evolution of the universe. Neutron stars are extremely dense stellar remnants formed from the collapsed cores of massive stars that have undergone supernova explosions. When a star with an initial mass typically between about 8 and 25 times that of the Sun exhausts its nuclear fuel, its core collapses under gravity. If the remaining core mass exceeds the limit for white dwarf stability, but is insufficient to form a black hole, protons and electrons are forced to combine into neutrons, producing a neutron star. A neutron star typically has a mass between about 1.1 and 2.3 times the mass of the Sun, but a radius of only about 10 to 12 kilometers. This compression results in densities comparable to those found in atomic nuclei, on the order of hundreds of trillions of grams per cubic centimeter. A single teaspoon of neutron star matter would weigh billions of tons on Earth. Gravity at the surface is so strong that escape velocities reach a significant fraction of the speed of light. The internal structure of a neutron star is layered and remains an active area of research. The outer crust consists of atomic nuclei arranged in a rigid lattice immersed in a sea of electrons. Deeper layers contain increasingly neutron-rich matter, and the inner core may contain exotic states such as superfluid neutrons, superconducting protons, or other forms of dense matter not found elsewhere in the universe. The exact composition depends on the star's mass and the physics of matter at extreme densities. Neutron stars are born extremely hot, with temperatures exceeding 1 trillion Kelvin immediately after formation. They cool rapidly through neutrino emission, and then more slowly through photon radiation over millions of years. Despite their cooling, neutron stars can remain detectable for long periods due to their strong magnetic fields and rapid rotation, which power various observable phenomena. Many neutron stars are observed as pulsars. These are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. If these beams sweep across Earth, they are detected as highly regular pulses of radiation. Pulsar rotation periods range from milliseconds to several seconds and can be measured with extraordinary precision. Over time, pulsars gradually slow down as they lose rotational energy. Magnetic fields in neutron stars are among the strongest known in the universe. Typical neutron star magnetic fields are trillions of times stronger than Earth's, while a subclass known as magnetars possess fields even stronger. These intense fields can fracture the star's crust, releasing large bursts of high-energy radiation. Magnetars are associated with powerful X-ray and gamma-ray flares. Neutron stars often exist in binary systems, where interactions with a companion can significantly alter their behavior. Accretion of matter from a companion can spin up a neutron star, producing millisecond pulsars with extremely rapid rotation. Such systems are also strong sources of X-rays. In some cases, two neutron stars orbit each other and eventually merge due to energy loss from gravitational wave emission. Neutron star mergers are of major astrophysical importance. When two neutron stars collide, they produce gravitational waves and electromagnetic radiation across multiple wavelengths. These events are also believed to be a primary site for the creation of many heavy elements, such as gold and platinum, through rapid neutron capture processes. As a result, neutron stars play a critical role in both fundamental physics and cosmic chemical evolution. Black holes formed from stars, known as stellar mass black holes, are the end states of the most massive stars. They originate when a star with an initial mass typically greater than about 20 times that of the Sun exhausts its nuclear fuel and undergoes core collapse. If the remaining core mass after a supernova explosion exceeds the maximum mass that neutron degeneracy pressure can support, gravity overwhelms all known forms of pressure, and the core collapses into a black hole. A defining feature of a black hole is the event horizon, a boundary beyond which nothing, including light, can escape. The size of the event horizon is described by the Schwarzschild radius, which depends only on the black hole's mass. For a stellar mass black hole, this radius is typically only a few tens of kilometers, even though the mass may exceed that of the Sun by many times. All of this mass is concentrated within an extraordinarily small volume. The collapse that forms a black hole occurs extremely rapidly, on timescales of milliseconds to seconds. During core collapse, the inner regions fall inward at a significant fraction of the speed of light. In some cases, the outer layers of the star are expelled in a supernova explosion, while in others the collapse may be so complete that little or no explosion occurs, a process sometimes referred to as direct collapse. Black holes themselves emit no light, but their presence can be detected through their gravitational influence on surrounding matter. In binary systems, a stellar mass black hole can accrete gas from a companion star. As this gas spirals inward, it forms an accretion disk that heats up due to friction and gravitational energy release, emitting intense X-rays. These emissions provide one of the primary observational signatures of stellar black holes. Accretion onto black holes is highly efficient at converting mass into energy. A significant fraction of the infalling material's rest mass can be released as radiation before crossing the event horizon. This efficiency exceeds that of nuclear fusion, making accreting black holes some of the most energetic objects in the universe. In some systems, powerful jets of particles are launched from regions near the black hole at relativistic speeds. Stellar mass black holes have masses ranging from a few times the Sun's mass up to several tens of solar masses. Their masses reflect the properties of their progenitor stars and the amount of material lost during stellar evolution and explosion. Observations of gravitational waves from merging black holes have revealed populations of stellar black holes more massive than previously expected, indicating that black hole formation depends strongly on metallicity and stellar environment. Black holes play an important role in the life cycles of stars and in galactic evolution. Their formation marks the final removal of massive stars from active nuclear burning. In binary systems, black holes can significantly affect their companions, stripping mass and altering stellar evolution. Over time, black hole mergers contribute to the growth of more massive black holes. Although black holes represent an endpoint of stellar evolution, they are not entirely static. They can gain mass through accretion and mergers, and in theory, they lose mass extremely slowly through Hawking radiation. For stellar mass black holes, this process is negligible on cosmic timescales, with evaporation times vastly exceeding the current age of the universe. The study of stellar black holes provides critical tests of gravity under extreme conditions. Observations of their formation, growth, and interactions help constrain models of stellar evolution, supernova physics, and the behavior of matter and spacetime in the strongest gravitational fields known. Stellar life cycles describe the sequence of physical changes a star undergoes from its formation to its final state. Although stars vary widely in mass and composition, their evolutionary paths follow well-defined principles governed primarily by mass. A star's initial mass determines its core temperature, fusion processes, luminosity, lifespan, and the nature of its death. As a result, stellar evolution is best understood as a set of mass-dependent pathways rather than a single universal sequence. All stars begin their lives in molecular clouds, where gravitational collapse produces protostars. Once core temperatures become high enough to ignite hydrogen fusion, the star enters the main sequence, the longest and most stable phase of its existence. During this stage, hydrostatic equilibrium is maintained as energy from fusion counterbalances gravity. The star's position on the main sequence reflects its mass, with higher mass stars being hotter and more luminous. As hydrogen in the core is gradually converted into helium, the internal composition of the star changes. When core hydrogen is depleted, fusion can no longer occur at the center. Gravity causes the core to contract and heat up, while hydrogen fusion continues in a surrounding shell. This transition marks the end of the main sequence phase and initiates expansion of the outer layers. From this point onward, stellar evolution diverges strongly depending on mass. Low and intermediate mass stars evolve into red giants. As the core contracts, temperatures eventually become high enough to ignite helium fusion, producing carbon and oxygen. Helium burning stabilizes the star temporarily. But once helium is exhausted, these stars lack sufficient mass to ignite further fusion stages. They shed their outer layers through stellar winds, forming planetary nebulae, while the core remains as a white dwarf supported by electron degeneracy pressure. High-mass stars experience a much more complex and violent evolution. After exhausting hydrogen and helium, their cores reach temperatures sufficient to fuse progressively heavier elements, including carbon, neon, oxygen, and silicon. This process forms a layered structure with multiple fusion shells. Fusion continues until iron accumulates in the core. Because iron fusion consumes energy rather than releasing it, no further stable fusion is possible. When an iron core exceeds a critical mass, it collapses catastrophically under gravity. This collapse triggers a core collapse supernova, one of the most energetic events in the universe. The explosion disperses the star's outer layers into space, enriching the interstellar medium with heavy elements. The fate of the collapsed core depends on its mass, forming either a neutron star or a black hole. Binary interactions can significantly modify stellar life cycles. Mass transfer between stars can strip outer layers, prolong fusion stages, or trigger explosive events such as novae and type Ia supernovae. Mergers between stars or stellar remnants can create objects that follow evolutionary paths different from those of isolated stars. As a result, stellar evolution in binary systems is more diverse and complex than in single-star models. Stellar life cycles operate on timescales ranging from millions to trillions of years. Massive stars live fast and die young, while low-mass stars evolve so slowly that none have yet reached their final stages. The cumulative effect of stellar evolution shapes galaxies by regulating energy output, recycling matter, and determining chemical composition. Understanding stellar life cycles is therefore essential for explaining the structure, history, and future evolution of the universe. Nuclear fusion is the process by which stars generate energy, by combining lighter atomic nuclei into heavier ones. This process occurs in stellar cores, where temperatures and pressures are sufficiently high to overcome the electrostatic repulsion between positively charged nuclei. Fusion converts a small fraction of mass into energy according to mass-energy equivalence, and this energy is responsible for a star's luminosity, internal pressure, and long-term stability. In most stars, nuclear fusion begins with hydrogen as the primary fuel. The simplest and most common fusion pathway is the proton-proton chain reaction, which dominates in low and intermediate mass stars. In this process, hydrogen nuclei fuse through a series of steps to form helium, releasing energy in the form of gamma rays, neutrinos, and kinetic energy of particles. The rate of this reaction is highly sensitive to temperature, increasing rapidly as core temperatures rise. In more massive stars, hydrogen fusion proceeds mainly through the carbon-nitrogen-oxygen cycle. This process uses carbon, nitrogen, and oxygen nuclei as catalysts to convert hydrogen into helium. Although the end result is the same as the proton-proton chain, the CNO cycle operates far more efficiently at higher temperatures. As a result, massive stars produce much greater energy output and luminosity than smaller stars. Fusion reactions in stellar cores generate enormous amounts of energy, but this energy does not escape immediately. Photons produced in the core undergo countless interactions with surrounding particles, taking thousands to millions of years to reach the star's surface. Energy is transported outward through radiation, convection, or a combination of both, depending on the star's mass and internal structure. Once the energy reaches the surface, it is emitted as starlight across the electromagnetic spectrum. As stars evolve, their fusion processes change. When hydrogen in the core is exhausted, fusion may continue in shells surrounding the core. In sufficiently massive stars, rising core temperatures allow the fusion of helium into carbon and oxygen, and later the fusion of heavier elements. Each successive fusion stage releases less energy and occurs over shorter timescales. The balance between energy production and gravitational contraction continues to regulate stellar structure. Fusion of elements heavier than iron does not produce net energy. Iron has the most tightly bound nucleus, so fusing iron consumes energy rather than releasing it. For this reason, stable fusion in stars effectively ends at iron. In massive stars, the accumulation of an iron core removes the primary source of pressure supporting the star, leading to gravitational collapse and supernova explosion. Nuclear fusion in stars is the primary source of elements heavier than hydrogen and helium in the universe. Through fusion and subsequent stellar explosions, stars create and distribute carbon, oxygen, silicon, and many other elements essential for planets and life. The material produced in one generation of stars becomes the raw material for the next, making fusion a central driver of cosmic chemical evolution. The study of stellar fusion relies on both theoretical modeling and observational evidence. Measurements of neutrinos emitted by the sun provide direct confirmation of ongoing fusion reactions. Stellar spectra, luminosities, and lifetimes are consistent with predictions based on nuclear physics. As a result, nuclear fusion is a well-established explanation for how stars generate energy and maintain their structure over vast periods of time. The light and color of stars are direct consequences of their surface temperatures and physical properties. Stars emit electromagnetic radiation across a broad range of wavelengths, but the distribution of that radiation depends primarily on temperature. Hotter stars emit more energy at shorter wavelengths, appearing blue or white, while cooler stars emit more energy at longer wavelengths, appearing red. This behavior closely follows the principles of blackbody radiation. Stellar color is quantified using surface temperature, which ranges from about 2,000 Kelvin for the coolest red stars to over 40,000 Kelvin for the hottest blue stars. Blue stars are not hotter because of their color. Rather, their color is a result of their high temperature. Similarly, red stars are cooler but not necessarily less massive. Color alone does not determine a star's size or evolutionary stage, only its surface temperature. The spectrum of a star provides detailed information about its physical conditions. When starlight is dispersed into a spectrum, it shows dark absorption lines caused by elements in the star's outer layers absorbing specific wavelengths. The pattern and strength of these lines depend on temperature, pressure, and chemical composition. Spectral analysis allows astronomers to determine a star's temperature, elemental makeup, surface gravity, and motion relative to Earth. Luminosity is the total amount of energy a star emits per unit time and is distinct from brightness as seen from Earth. Apparent brightness depends on both luminosity and distance, while intrinsic luminosity reflects the star's actual energy output. Two stars with the same color and temperature can have very different luminosities if their sizes differ significantly. Large stars radiate more energy than small stars at the same temperature because they have greater surface area. Energy generated in the stellar core reaches the surface through radiation and convection, shaping the observed light output. In radiative zones, energy moves outward as photons that are repeatedly absorbed and re-emitted. In convective zones, energy is carried by the physical motion of hot plasma rising and cooler plasma sinking. These processes influence surface features and can affect variability in brightness. Some stars exhibit changes in brightness over time. These variations can be caused by pulsations, surface activity, eclipses in binary systems, or explosive events such as flares. Pulsating stars expand and contract periodically, causing predictable changes in temperature and luminosity. Other stars show irregular variability linked to magnetic activity or mass loss. Studying these variations provides insight into stellar interiors and evolution. Interstellar material affects the observed color and brightness of stars. Dust between stars scatters and absorbs light more effectively at shorter wavelengths, causing distant stars to appear redder and dimmer than they truly are. This effect, known as interstellar reddening, must be corrected to accurately determine stellar properties. Infrared observations are often used to peer through dust and reveal stars hidden at visible wavelengths. Stellar light also carries information about motion. Through the Doppler effect, shifts in spectral lines reveal whether a star is moving toward or away from Earth. Rotational motion can broaden spectral lines, while orbital motion in binary systems produces periodic shifts. These measurements allow precise determination of stellar velocities, masses, and orbital parameters. Stellar motion refers to the various ways stars move through space, including their rotation, orbital motion in systems, and travel through the galaxy. Although stars appear fixed relative to one another on short timescales, they are in constant motion governed by gravity. These motions provide critical information about stellar masses, galactic structure, and the dynamics of the universe. Stars rotate about their own axes. Rotation rates vary widely and depend on mass, age, and evolutionary state. Massive, young stars often rotate rapidly, while older, low-mass stars tend to rotate more slowly due to angular momentum loss through stellar winds. Rotation influences a star's shape, causing rapid rotators to become oblate, and affects internal mixing, magnetic field generation, and surface activity. Orbital motion occurs when stars are part of binary or multiple systems. In such systems, stars orbit their common center of mass according to the laws of gravity. Orbital periods can range from minutes to thousands of years, depending on separation and mass. Measurements of orbital motion allow direct determination of stellar masses, making binary stars essential for testing models of stellar structure and evolution. Stars also move through the galaxy on large scales. Each star follows an orbit around the galactic center determined by the combined gravitational influence of visible matter and dark matter. In the Milky Way, Stars orbit the galactic center at speeds of hundreds of kilometers per second. These orbits are not perfectly circular and can change over time due to gravitational interactions with other stars and structures. Proper motion describes a star's apparent movement across the sky relative to more distant background objects. It is measured in angular displacement per year and depends on both the star's true velocity and its distance from Earth. Nearby stars generally exhibit larger proper motions than distant ones. Proper motion measurements, combined with distance estimates, provide the transverse component of a star's space velocity. Radial velocity refers to motion along the line of sight, either toward or away from the observer. It is measured using the Doppler shift of spectral lines. When combined with proper motion, radial velocity completes the three-dimensional description of a star's motion through space. These measurements are critical for studying stellar kinematics, detecting unseen companions, and mapping galactic dynamics. Stellar motion is influenced by gravitational interactions over time. Close encounters between stars can alter trajectories, particularly in dense environments such as star clusters. In extreme cases, stars can be ejected at very high speeds, becoming runaway or hypervelocity stars that travel through or even escape the galaxy. Such objects provide insight into strong gravitational interactions and the distribution of mass in galaxies. Rotation and motion also evolve as stars age. As stars lose mass and angular momentum through winds and interactions, their rotation rates and orbits can change. In binary systems, tidal forces can synchronize rotation with orbital motion or lead to mass transfer. These processes play a significant role in shaping stellar evolution and observable behavior. The study of stellar motion underpins much of modern astronomy. It allows precise determination of stellar masses, distances, and ages, and reveals the large-scale structure and history of galaxies. By tracking how stars move individually and collectively, astronomers gain insight into the forces that govern cosmic systems across vast scales of space and time. Systems in which two or more stars are gravitationally bound and orbit a common center of mass. They are not rare exceptions, but a dominant outcome of star formation, especially for massive stars. Observations show that a large fraction of stars in the Milky Way belong to binaries or higher-order systems, indicating that stellar companionship is a natural consequence of how molecular clouds fragment during collapse. Binary systems are classified based on how they are detected and observed. Visual binaries are systems where both stars can be individually resolved with telescopes, allowing their orbital motion to be directly tracked over time. Spectroscopic binaries are too close to be visually separated, but their orbital motion is revealed through periodic Doppler shifts in their spectral lines. Eclipsing binaries are oriented such that one star passes in front of the other from Earth's perspective, producing regular dips in brightness. Astrometric binaries are identified when a visible star shows a wobble caused by an unseen companion. In a binary system, the two stars orbit their common center of mass, which lies closer to the more massive star. The orbital properties, such as period and separation, are governed by gravity and follow the same physical principles as planetary motion. Measurements of binary orbits provide one of the most accurate methods for determining stellar masses, a fundamental parameter that cannot be directly measured for isolated stars. This makes binary systems crucial for testing models of stellar structure and evolution. Multiple star systems extend this concept to three or more stars, often arranged in hierarchical configurations. A common arrangement is a close binary pair orbited by a more distant third star. Such hierarchical systems are dynamically stable over long timescales, whereas systems with several stars at similar separations tend to be unstable and may eject one or more members over time. The ejected stars can become high-velocity or runaway stars, moving independently through the galaxy. Interactions within binary and multiple systems can significantly alter stellar close binaries, mass transfer can occur when one star expands and overflows its gravitational boundary, allowing material to flow onto its companion. This process can change stellar lifetimes, surface compositions, and luminosities. In extreme cases, mass transfer leads to the formation of exotic objects such as X-ray binaries, where matter falling onto a compact object releases intense radiation. Binary systems are also the origin of several important astrophysical phenomena. Certain types of supernovae occur only in binary systems, particularly when a white dwarf accretes matter from a companion until it reaches a critical mass. Gravitational wave sources detected on Earth often involve pairs of compact objects, such as neutron stars or black holes, formed through the evolution of massive binary systems. Without binaries, these events would be far rarer or impossible. Well-known nearby examples illustrate the diversity of stellar companionship. Alpha Centauri is a triple system consisting of a close binary and a more distant third star, making it the closest stellar system to the Sun. Sirius is a binary composed of a main sequence star and a white dwarf companion, providing direct evidence that stars can evolve into compact remnants while remaining gravitationally bound. Binary and multiple star systems also play a major role in planet formation and dynamics. Planets can orbit one star in a wide binary, both stars in a close pair, or exist in more complex configurations influenced by multiple gravitational sources. The presence of companion stars can affect disk stability, planet migration, and long-term orbital stability, making such systems important laboratories for understanding planetary diversity. Overall, binary and multiple star systems are not special cases, but fundamental building blocks of stellar populations. They provide the best measurements of stellar masses, reveal pathways to extreme astrophysical events, and demonstrate that stellar evolution is often shaped by interaction rather than isolation. Understanding stars as members of systems, rather than solitary objects, is essential for an accurate picture of how stars live, change, and influence the universe. Variable stars are stars whose observed brightness changes over time due to physical processes occurring within the star or geometric effects related to its orientation. These variations can range from fractions of a percent to changes of several magnitudes, and can occur over timescales from milliseconds to years. Variability is a common stellar property and provides critical information about stellar structure, evolution, and distance measurement. Intrinsic variable stars change brightness because of processes within the star itself. One major class is pulsating variable stars, which expand and contract in a regular or semi-regular manner. These pulsations are driven by imbalances between gravity and internal pressure, often regulated by changes in opacity in specific layers of the stellar interior. As the star expands, it cools and dims. As it contracts, it heats up and brightens, producing periodic light variations. Pulsating variables include several well-studied types distinguished by mass, age, and evolutionary stage. Some pulsate with highly regular periods that are directly related to their intrinsic luminosity. This period-luminosity relationship allows astronomers to determine their true brightness, and by comparing it to observed brightness, calculate distances. Such stars are essential tools for mapping the scale of the Milky Way and nearby galaxies. Another category of intrinsic variables consists of eruptive stars, whose brightness changes due to sudden releases of energy or mass. These include stars that undergo flares, strong stellar winds, or surface instabilities. In these cases, variability is often irregular and linked to magnetic activity or rapid evolutionary changes. Young stars, in particular, can show strong variability as they accrete material from surrounding disks. Extrinsic variable stars change brightness not because the star itself is changing, but due to external effects. The most important group in this category is eclipsing binary systems, where two stars orbit each other and periodically pass in front of one another from the observer's viewpoint. When one star blocks part or all of the other's light, the total brightness drops in a predictable pattern. Analysis of these light curves reveals stellar sizes, masses, and orbital parameters with high precision. Rotating variable stars form another extrinsic class. These stars have uneven surface brightness, often caused by star spots, chemical patches, or magnetic activity. As the star rotates, brighter and darker regions move in and out of view, producing regular brightness variations tied to the rotation period. Such variability provides direct measurements of stellar rotation rates and surface activity. Variable stars play a crucial role in astrophysics because they offer rare probes of stellar interiors. The pulsation frequencies of some variables can be analyzed in detail, allowing astronomers to infer internal density, temperature profiles, and core properties. This technique, known as asteroseismology, is comparable to how seismology reveals Earth's internal structure and has significantly refined models of stellar physics. The study of variable stars also underpins the cosmic distance scale. Certain variable stars serve as standard candles, meaning their intrinsic brightness can be determined from observable properties such as pulsation period. These measurements have been fundamental in establishing distances to star clusters, galaxies, and ultimately in determining the expansion rate of the universe. Variability is closely linked to stellar evolution. Stars often become variable during transitional phases, such as when they leave the main sequence or approach the end of their lives. Observing variability across different stellar populations helps astronomers trace how stars change over time and how physical processes differ with mass and composition. In summary, variable stars are not anomalies, but key indicators of dynamic stellar behavior. Their brightness changes reveal internal physics, orbital geometry, magnetic activity, and evolutionary state. Without the study of variable stars, modern understanding of stellar structure, galactic scale, and cosmic distances would be severely limited. Supernovae are powerful stellar explosions that mark the end of certain stars' lives and release enormous amounts of energy in a very short time. During a supernova, a star can briefly shine as brightly as an entire galaxy, emitting more energy in seconds than the sun will produce over its entire lifetime. These events are rare on a galactic scale, but critically important for the physical and chemical evolution of the universe. There are two main physical pathways that lead to supernovae. One involves massive stars, typically more than about 8 times the mass of the sun, that exhaust their nuclear fuel. When fusion in the core can no longer generate enough pressure to counteract gravity, the core collapses rapidly. This collapse triggers a violent rebound and shock wave that expels the star's outer layers into space, leaving behind a neutron star or black hole. These are known as core collapse supernovae. The second pathway occurs in binary systems involving white dwarfs. A white dwarf can pull matter from a companion star over time. If it gains enough mass to approach a critical limit, its internal pressure can no longer support stable nuclear reactions. This leads to a runaway thermonuclear explosion that completely disrupts the white dwarf. In this case, no compact remnant remains. These thermonuclear supernovae have remarkably uniform peak brightness, making them valuable tools for distance measurement. Supernovae dramatically reshape their surroundings. The expelled material expands outward at thousands of kilometers per second, forming a supernova remnant composed of hot gas, shock waves, and high-energy particles. These remnants interact with surrounding interstellar material, compressing gas clouds, and sometimes triggering new episodes of star formation. In this way, stellar death contributes directly to the birth of future generations of stars. One of the most significant consequences of supernovae is the creation and distribution of heavy elements. Elements heavier than iron cannot be produced efficiently by normal stellar fusion. because such reactions consume energy rather than release it. The extreme temperatures and pressures during supernova explosions enable rapid nuclear reactions that form many of these heavy elements. The explosion then disperses them into interstellar space, enriching future stars, planets, and eventually living systems. Supernovae are also major sources of high-energy radiation and particles. They produce intense bursts of neutrinos, which escape directly from the collapsing core and provide direct information about processes deep inside the star. They also accelerate charged particles to near-light speeds, contributing to cosmic rays that permeate the galaxy. These energetic outputs influence the physical state of the interstellar medium over large distances. Observationally, supernovae are classified based on their spectra and light curves. Differences in the presence or absence of certain elements, as well as how brightness changes over time, reflect differences in progenitor stars and explosion mechanisms. Careful monitoring of these properties allows astronomers to reconstruct the star's mass, composition, and evolutionary history prior to the explosion. Supernovae have played a key role in advancing cosmology. Because certain types have predictable intrinsic brightness, they can be used to measure distances across vast cosmic scales. Observations of distant supernovae have revealed that the expansion of the universe is accelerating, a discovery that reshaped modern cosmological models and our understanding of large-scale cosmic evolution. Although destructive on a local scale, supernovae are essential to cosmic renewal. They regulate star formation, redistribute matter and energy, and drive chemical evolution across galaxies. Without supernova explosions, the universe would lack many of the elements necessary for rocky planets, complex chemistry, and life as it exists today. Stars are the primary factories for creating the chemical elements that make up the visible universe. In the early universe, only the lightest elements existed in significant amounts, mainly hydrogen and helium, with trace amounts of lithium. All heavier elements were produced later through nuclear processes, inside stars, and during stellar explosions. This gradual enrichment of matter is known as stellar nucleosynthesis and is fundamental to the formation of planets, atmospheres, and life. Inside stars, elements are created through nuclear fusion, a process in which lighter atomic nuclei combine to form heavier ones while releasing energy. In main sequence stars like the Sun, hydrogen nuclei fuse to form helium in the core. This reaction is the dominant energy source for most of a star's lifetime. The rate of fusion depends on temperature, pressure, and mass, meaning more massive stars burn fuel faster and reach more advanced stages of element production. As stars evolve and their cores heat up, they can begin fusing heavier elements. After hydrogen is depleted in the core, helium fusion can occur, producing carbon and oxygen. In more massive stars, this process continues through successive stages, forming elements such as neon, magnesium, silicon, sulfur, and calcium. Each fusion stage requires higher temperatures and occurs over progressively shorter timescales as the star approaches the end of its life. Fusion inside stars can only efficiently produce elements up to iron. Iron represents a turning point in nuclear physics because fusing iron nuclei does not release energy. Instead, it consumes energy. Once a stellar core becomes dominated by iron, fusion can no longer support the star against gravitational collapse. This limitation explains why normal stellar interiors cannot create elements heavier than iron in large quantities. Elements heavier than iron are primarily formed during extreme astrophysical events. Supernova explosions provide the necessary energy and particle densities for rapid nuclear reactions that build very heavy elements. During these events, atomic nuclei rapidly capture neutrons and then decay into stable heavy elements. This process is responsible for creating many elements such as gold, platinum, uranium, and other rare but important components of matter. Some heavy elements are also produced more gradually in and certain evolved stars. In these stars, slower neutron capture reactions occur over long periods, creating elements heavier than iron in a step-by-step manner. These elements are later released into space through stellar winds, contributing to the chemical enrichment of the interstellar medium even before a supernova occurs. Once created, elements are distributed into space through stellar winds, planetary nebulae, and supernova explosions. This material mixes with interstellar gas and dust, forming new molecular clouds that will eventually collapse to form new stars and planetary systems. Each generation of stars, therefore, contains a higher proportion of heavy elements than the generation before it, a trend observed throughout the history of the galaxy. The chemical composition of stars reveals their age and origin. Older stars generally contain fewer heavy elements because they formed before the universe was significantly enriched. Younger stars, including the Sun, formed from material that had already been processed by multiple earlier generations of stars. By analyzing stellar spectra, astronomers can trace how and where elements were created and dispersed over cosmic time. Element creation in stars directly connects astrophysics to everyday matter. The carbon in living organisms, the oxygen we breathe, the calcium in bones, and the iron in blood were all formed in stellar interiors or stellar explosions long before the Earth existed. Stellar nucleosynthesis explains not only the diversity of elements in the universe, but also why matter capable of forming complex structures exists at all. In summary, stars are responsible for transforming simple primordial matter into the rich chemical variety observed today. Through fusion during their lifetimes and explosive processes at their deaths, stars continuously manufacture and recycle elements. Without this ongoing stellar production of elements, planets, complex chemistry, and life would not be possible anywhere in the universe. Measuring the distance to stars is one of the fundamental challenges in astronomy because stars are far beyond the reach of direct physical measurement. Astronomers determine stellar distances by analyzing how starlight behaves as it travels through space, and how a star's apparent properties change when viewed from different locations or compared to known physical standards. Accurate distance measurements are essential for determining a star's true brightness, size, and role in galactic structure. The most direct and reliable method for measuring distances to nearby stars is parallax. Parallax is the apparent shift in a star's position against the background of more distant stars as Earth moves around the Sun. By observing this shift at opposite points in Earth's orbit and measuring the tiny angle involved, astronomers can calculate the star's distance using simple geometry. The smaller the parallax angle, the farther away the star is. Parallax measurements are extremely precise for nearby stars, but become ineffective at large distances because the angles involved become too small to measure accurately. Even for the closest stars, these angles are fractions of an arcsecond. As a result, parallax is primarily used to measure distances within a limited region of the Milky Way. But within that range, it provides a direct, assumption-free distance scale. For stars beyond the reach of parallax, astronomers rely on indirect methods based on intrinsic stellar properties. One key approach involves standard candles, which are objects whose true luminosity can be determined from observable characteristics. By comparing a star's intrinsic brightness to how bright it appears from Earth, its distance can be calculated using the inverse square law of light, which describes how brightness decreases with distance. Certain types of stars serve as especially reliable standard candles. These stars exhibit regular relationships between measurable properties and true luminosity. Once these relationships are calibrated using nearby stars with known parallax distances, they can be applied to much more distant stars and star systems. This method extends distance measurements far beyond the limits of direct geometric techniques. Another important distance measurement technique is spectroscopic parallax, despite its name not involving actual parallax. In this method, a star's spectrum is analyzed to determine its temperature, composition, and luminosity class. From these properties, astronomers estimate the star's true luminosity. Comparing this to the observed brightness yields an approximate distance. This method depends on accurate stellar models and is less precise than geometric parallax, but useful for large numbers of stars. Distances to stars within clusters can also be estimated by comparing their positions on diagrams that relate brightness and temperature. Since stars in a cluster formed at roughly the same time and distance, patterns in these diagrams reveal how far away the entire group is. This approach helps determine distances to star clusters that are too distant for individual parallax measurements. Interstellar dust complicates distance measurements by absorbing and scattering light, making stars appear dimmer and redder than they truly are. If this effect is not corrected, stars can appear farther away than they actually are. Astronomers account for this by measuring reddening effects and modeling how dust is distributed between Earth and the observed stars. Accurate stellar distances form the foundation of the cosmic distance ladder, a sequence of overlapping measurement techniques that build upon one another. Parallax anchors the nearby scale. Standard candles extend measurements across the galaxy and beyond, and other methods continue outward to distant galaxies. Errors at the lower rungs propagate upward, making precise stellar distance measurements critically important for all of astronomy. Knowing stellar distances allows astronomers to calculate true luminosities, determine stellar sizes, estimate ages, and map the structure of the Milky Way. It also enables comparisons between stars in different regions of the galaxy and reveals large-scale features such as spiral arms and stellar populations. Without reliable distance measurements, stars would be reduced to points of light with uncertain physical meaning. In summary, measuring the distance to stars relies on a combination of geometric techniques, physical models, and calibrated reference objects. Each method has limits and uncertainties, but together they provide a coherent and tested framework for mapping the universe. Stellar distance measurement transforms observations into physical understanding and underpins nearly every major conclusion in modern astrophysics. Nearby stars are those located within a few tens of light years of the Sun and form the Sun's immediate stellar neighborhood within the Milky Way. Studying these stars is essential because their proximity allows precise measurements of distance, motion, mass, and composition. Nearby stars provide the benchmark data used to calibrate stellar models and to understand the broader stellar population of the galaxy. The closest known stellar system to the Sun is Alpha Centauri, located just over 4 light-years away. It is a multiple star system consisting of 2 sun-like stars orbiting each other and a smaller red dwarf companion. Because of its proximity, it has been extensively studied for stellar dynamics, composition, and the potential presence of planets. Precise measurements of its motion also help refine models of stellar orbits within the Milky Way. The nearest individual star to the Sun is Proxima Centauri, a red dwarf member of the Alpha Centauri system. Red dwarfs dominate the nearby stellar population because they are the most common type of star in the galaxy. Although faint compared to the Sun, their long lifespans and abundance make them important contributors to galactic structure and evolution. Their proximity allows detailed study of stellar flares, magnetic activity, and star-planet interactions. The brightest star in Earth's night sky is Sirius, located about 8.6 light-years away. Its apparent brightness is due to both its intrinsic luminosity and its relative closeness. Sirius is a binary system composed of a main sequence star and a white dwarf companion. Observations of this system provided early confirmation that stars can evolve into compact remnants while remaining gravitationally bound to a companion. Another notable nearby star is Barnard's star, a red dwarf located roughly 6 light-years from the Sun. It is known for having one of the highest measured proper motions, meaning it appears to move rapidly across the sky relative to more distant stars. This motion reflects both its proximity and its actual high velocity through the galaxy, offering insight into stellar kinematics and galactic dynamics. Vega is another well-studied nearby star, located about 25 light-years away. It has served as a reference point for brightness measurements in astronomy and has been used to define photometric calibration systems. Observations of surrounding dust indicate the presence of a debris disk, providing evidence that planet formation processes occur around stars more massive than the Sun. The nearby stellar neighborhood includes stars of many different types, but low-mass red dwarfs dominate by number. Sun-like stars are less common, and massive, short-lived stars are rare or absent nearby because they evolve quickly and do not persist long enough to remain close unless they formed very recently. This distribution reflects both stellar lifetimes and the history of star formation in the local region of the galaxy. Nearby stars are also prime targets in the search for exoplanets. Their closeness allows small planetary signals to be detected more easily than around distant stars. Measurements of stellar wobble, brightness dips, and direct imaging are all more effective at short distances. As a result, many of the best characterized exoplanet systems orbit nearby stars, shaping understanding of planetary system diversity. The motions of nearby stars relative to the Sun reveal the structure and dynamics of the Milky Way. By tracking their velocities and trajectories, astronomers can infer the gravitational influence of the galaxy and identify groups of stars that share a common origin. Some nearby stars are passing through the solar neighborhood temporarily, while others formed in roughly the same region as the Sun. In summary, famous nearby stars are scientifically important not because of their fame, but because their proximity allows detailed and precise study. They anchor stellar physics, calibrate distance and brightness scales, and provide critical insight into stellar evolution and planetary systems. Understanding the nearest stars establishes the foundation for interpreting all more distant stellar observations. The Sun is a typical example of a main sequence star, classified as a G-type star based on its surface temperature and spectral characteristics. It is composed primarily of hydrogen and helium and generates energy through nuclear fusion in its core. In terms of mass, size, and luminosity, the Sun falls near the middle of the stellar range, making it neither unusually small nor exceptionally large when compared to the full diversity of stars in the galaxy. With a mass of about 1 solar mass by definition, the Sun contains more than 99% of the total mass of the solar system. Its gravity governs the motions of planets, asteroids, comets, and dust. The Sun's radius and luminosity output place it well above the smallest stars, such as red dwarfs, but far below giant and supergiant stars, which can be hundreds or thousands of times larger and brighter. The surface temperature of the Sun is approximately 5,800 Kelvin, giving it a yellow-white appearance. This temperature is higher than that of red dwarfs, but lower than that of hotter stars such as A-type and O-type stars, which emit much more energy and appear blue-white. The Sun's moderate temperature contributes to its long and stable lifespan, allowing it to burn hydrogen steadily for billions of years. The Sun is currently about halfway through its main sequence lifetime, which is expected to last roughly 10 billion years in total. More massive stars consume their fuel much faster and may live for only millions of years, while less massive stars can remain stable for trillions of years. The Sun's intermediate mass gives it a balance between longevity and energy output that is favorable for the long-term stability of planetary systems. In terms of luminosity, the Sun is brighter than the vast majority of stars in the Milky Way, since most stars are faint red dwarfs. However, it is far less luminous than giant and supergiant stars, which dominate the light of distant galaxies despite being relatively rare. This distinction highlights the difference between numerical dominance and energetic dominance in stellar populations. The sun's internal structure is typical of stars of its mass. Energy is produced in the core through hydrogen fusion, transported outward by radiation and convection, and finally emitted from the surface as light and other forms of electromagnetic radiation. This structure closely matches theoretical models of stellar physics and serves as the primary reference point for understanding other stars. Compared to many stars, the sun is unusually well studied due to its proximity. Its surface features, magnetic activity, and internal oscillations can be observed in great detail. These observations allow astronomers to test theories of stellar behavior that cannot be directly verified for distant stars. As a result, much of modern stellar astrophysics is anchored to detailed knowledge of the sun. The sun also differs from many stars in having a well-developed planetary system with rocky planets, gas giants, and smaller bodies. While planets are now known to be common around other stars, the specific architecture of the solar system reflects the sun's mass, composition, and formation environment. Comparing the sun to other planet-hosting stars helps identify which aspects of the solar system are typical and which are unusual. From a galactic perspective, the sun is an ordinary star located in the disk of the Milky Way, orbiting the galactic center at a moderate distance. It is not associated with a dense star cluster and does not occupy a special position within the galaxy. Its motion and composition indicate that it formed from material enriched by earlier generations of stars. In summary, the sun is best described as a representative mid-sized star rather than an extreme one. Its mass, temperature, and luminosity place it near the center of the main sequence population. Understanding how the sun compares to other stars provides essential context for stellar evolution, planetary system formation, and the conditions that allow stable environments to persist over long periods of time. Star clusters are groups of stars that formed from the same molecular cloud and remain gravitationally associated for some period of time. Because the stars in a cluster share a common origin, they are approximately the same age and chemical composition, differing mainly in mass. This makes star clusters essential laboratories for studying stellar evolution, since differences among member stars can be attributed primarily to mass rather than age or environment. There are two main types of star clusters: open clusters and globular clusters. Open clusters are relatively small, loosely bound groups containing from a few dozen to a few thousand stars. They are typically found in the disk of the Milky Way and are closely associated with regions of recent or ongoing star formation. Their loose gravitational binding makes them vulnerable to disruption by galactic tidal forces and close encounters with other stars or molecular clouds. Open clusters are generally young on astronomical timescales, with ages ranging from a few million to a few billion years. Because their stars form together, open clusters often still contain massive, bright stars that have not yet exhausted their nuclear fuel. Over time, internal motions and external gravitational influences gradually disperse these stars into the galactic field, meaning most open clusters do not survive for the full lifetime of the galaxy. Globular clusters are much larger and more tightly bound than open clusters, containing tens of thousands to millions of stars packed into a roughly spherical shape. They are found primarily in the halo of the Milky Way, orbiting far above and below the galactic disk. Their strong gravitational binding allows them to remain intact for billions of years, making them among the oldest known stellar systems. Stars in globular clusters are typically very old, often more than 10 billion years in age. They formed early in the history of the galaxy, before it was significantly enriched with heavy elements. As a result, globular cluster stars generally have low metallicity compared to younger stars in the galactic disk. This chemical simplicity provides insight into the conditions that existed in the early universe. The high stellar density in globular clusters leads to frequent gravitational interactions between stars. These interactions can alter stellar orbits, create unusual binary systems, and even result in stellar collisions in the densest regions. Such environments produce exotic objects, including millisecond pulsars and compact binary systems that are rare outside clusters. Star clusters are crucial tools for testing theories of stellar evolution, because all stars in a cluster are at essentially the same distance. Differences in observed brightness directly reflect differences in intrinsic luminosity. By plotting cluster stars according to brightness and temperature, astronomers can trace how stars of different masses evolve over time and compare observations with theoretical models. Clusters also play an important role in measuring cosmic distances. The known properties of stars within clusters allow astronomers to estimate cluster distances and use them to calibrate other distance measurement methods. In particular, clusters help refine the relationships between stellar brightness, temperature, and age that are applied throughout the galaxy. Some clusters are visible to the naked eye and have been observed since antiquity. The Pleiades is a nearby open cluster that demonstrates how young stars can remain grouped for a time after their formation. In contrast, massive globular clusters contain stars that have remained bound since the early epochs of galactic history, illustrating the long-term stability possible in dense stellar systems. In a broader context, star clusters trace the structure and history of galaxies. The distribution, age, and composition of clusters reveal patterns of star formation and chemical enrichment over time. Open clusters map recent star formation in galactic disks, while globular clusters preserve records of early galactic assembly. In summary, star clusters are fundamental building blocks of stellar populations. Open clusters reveal how stars form and disperse in galactic disks, while globular clusters preserve ancient stellar populations in dense, long-lived systems. Together, they provide some of the clearest and most reliable evidence for how stars evolve and how galaxies develop across cosmic time. Stars and planets are closely linked through a shared formation process that begins in collapsing clouds of gas and dust. When a molecular cloud contracts under gravity, most of the material accumulates at the center to form a star, while the remaining material settles into a rotating disk around it. This structure, known as a protoplanetary disk, is the environment in which planets, moons, asteroids, and comets form. Protoplanetary disks consist primarily of hydrogen and helium gas, along with heavier elements in the form of dust grains. These dust particles collide and stick together, gradually growing from microscopic sizes into larger bodies called planetesimals. Over time, planetesimals can merge through further collisions and gravitational attraction, forming planetary embryos and eventually full-sized planets. This process occurs while the central star is still young and evolving. The properties of the host star strongly influence planet formation. Stellar mass affects disk mass, temperature, and lifetime. More massive stars tend to have hotter, shorter-lived disks, which can limit the time available for planet formation. Lower mass stars often have longer-lived disks, allowing extended periods for planetary growth. Stellar radiation and winds also shape disk evolution by heating, dispersing, or eroding disk material. Planets can form in different regions of the disk, leading to distinct planetary types. Close to the star, high temperatures allow only rocky materials to remain solid, resulting in the formation of terrestrial planets. Farther out, cooler conditions permit ices to form, enabling the growth of large solid cores that can capture thick atmospheres of gas and become gas giants or ice giants. The boundary between these regions depends on the star's luminosity and age. Not all planets remain where they form. Interactions between young planets and the surrounding disk can cause planetary migration, moving planets inward or outward over time. Gravitational interactions between multiple planets can also alter orbits, leading to eccentric paths or even ejection from the system. These processes help explain the wide diversity of planetary systems observed, many of which differ significantly from the architecture of the solar system. Observations have revealed that planets are common around stars of many types. Planets have been detected orbiting stars ranging from small red dwarfs to stars more massive than the Sun. The likelihood of planet formation is influenced by stellar composition, particularly the abundance of elements heavier than helium. Stars with higher metal content are more likely to host giant planets, reflecting the need for solid material during early planet formation. Stars and planets also interact after formation. Stellar radiation and magnetic activity can affect planetary atmospheres, especially for planets in close orbits. Intense radiation can strip atmospheres over time, altering planetary composition and habitability. Conversely, massive planets can influence their host stars through tidal interactions, slightly modifying stellar rotation or activity in certain cases. Young stars often show evidence of ongoing planet formation through gaps, rings, and spirals observed in their surrounding disks. These structures are interpreted as signs of forming planets interacting with disk material. As the system ages, the disk dissipates, leaving behind a mature planetary system and a star that continues its independent evolution. Planetary systems can exist in a wide range of configurations, including systems around single stars, binary stars, and even multiple star systems. In binary systems, planets may orbit one star or both stars together, depending on orbital separations. The gravitational influence of companion stars can affect disk stability and planet formation, but does not prevent planets from forming altogether. In summary, stars and planets form together as parts of the same physical process. The star provides the gravitational center and energy source, while the surrounding disk supplies the raw material for planets. Differences in stellar mass, composition, and environment lead to the immense diversity of planetary systems observed. Understanding stars is therefore essential for understanding how planets form, evolve, and persist throughout the galaxy. Observing stars is equivalent to looking back in time, because light travels at a finite speed. When astronomers observe a star that is 10 light-years away, they are seeing it as it existed 10 years in the past. For more distant stars, this time delay becomes increasingly significant, turning telescopes into tools for studying the history of the universe rather than its present state. This effect, known as look-back time, applies to all astronomical observations beyond the solar system. Even the light from the nearest stars left its source years ago, while light from distant regions of the Milky Way may have been traveling for tens of thousands of years. For stars in other galaxies, the light can be millions or billions of years old, revealing conditions that existed long before Earth formed. Ancient starlight provides direct evidence of how stars and galaxies evolved over cosmic time. By comparing nearby stars to distant ones, astronomers can identify differences in chemical composition, structure, and distribution. Distant stars tend to show lower abundances of heavy elements, reflecting an earlier stage of cosmic chemical enrichment, when fewer generations of stars had existed to produce and distribute these elements. The spectra of ancient starlight carry detailed information about the physical state of stars in the past. Absorption and emission lines reveal temperature, composition, motion, and density. Because these spectral features are preserved during light's journey through space, astronomers can analyze them to reconstruct stellar properties long after the light was emitted. One important consequence of observing ancient starlight is the ability to study early stellar populations. Some stars observed today formed during the early epochs of the universe and still survive, especially low-mass stars with extremely long lifespans. Their light contains signatures of the conditions under which they formed, providing clues about the first stages of star formation in galaxies. Ancient starlight also reveals how galaxies assembled and changed shape over time. The distribution of stars at different distances shows how star formation rates varied in the past. Regions seen at earlier times may show intense star formation, while closer regions reflect more recent, calmer phases. This allows astronomers to map the growth and aging of galactic structures. The expansion of the universe further affects ancient starlight through redshift. As space expands, the wavelength of light traveling through it is stretched, shifting it toward the red end of the spectrum. The amount of redshift provides a measure of how long the light has been traveling, and therefore how far back in time the observation reaches. This principle allows astronomers to place stars and galaxies within a precise cosmic timeline. Ancient starlight is also essential for testing models of stellar evolution. By observing stars at different stages of development across vast distances, astronomers effectively observe many evolutionary phases at once. This compensates for the fact that individual stars evolve far too slowly for most changes to be observed directly within a human lifetime. The faintness of ancient starlight poses significant observational challenges. Light from distant stars spreads out over enormous distances, making it extremely weak by the time it reaches Earth. Sensitive detectors, long exposure times, and advanced data processing are required to extract meaningful information. Despite these difficulties, even very weak starlight can provide reliable data about early cosmic conditions. Ancient starlight also connects cosmology with stellar physics. The properties of distant stars help constrain models of the universe's age, expansion history, and matter content. By comparing observations with theoretical predictions, astronomers refine estimates of when the first stars formed and how quickly the universe evolved from simplicity to complexity. In summary, ancient starlight allows astronomers to directly observe the past rather than infer it indirectly. Each photon carries information from a specific moment in cosmic history, preserved across immense distances. By collecting and analyzing this light, astronomy becomes a time-based science, revealing how stars, galaxies, and the universe itself have changed over billions of years. Stars have played a central role in human cultures for as long as people have observed the night sky. Long before modern science, stars were used as reliable reference points because their positions appeared fixed relative to one another over human timescales. This apparent stability made stars essential for navigation, timekeeping, and the organization of social and agricultural life. Early civilizations carefully tracked the motions of stars and recognized repeating patterns. Constellations were created by grouping stars into recognizable shapes, serving as mnemonic tools to remember their position and seasonal appearances. These patterns varied between cultures, reflecting local geography, beliefs, and social structures, but the underlying observations were based on the same sky shared by all humans. Stars were crucial for navigation, especially before the development of modern instruments. By observing the positions of specific stars relative to the horizon, travelers could determine direction and latitude. In the northern hemisphere, the near-fixed position of the North Star made it a stable reference for determining north. Similar techniques were used in the southern hemisphere, with different stellar references. Oceanic cultures developed highly sophisticated star-based navigation systems that enabled long-distance travel without maps or compasses. Calendars were another major application of stellar observation. The rising and setting of certain stars at specific times of the year provided a reliable way to mark seasons. These observations helped determine when to plant crops, harvest, or prepare for seasonal floods or droughts. Because stellar cycles are highly regular, star-based calendars were often more accurate over long periods than lunar calendars alone. Stars matter because they are the primary engines that shape the physical, chemical, and structural evolution of the universe. Nearly every large-scale feature observed in galaxies, from their light output to their chemical composition, is directly linked to stellar processes. Without stars, the universe would consist mostly of diffuse gas with little structure or complexity. Stars are the main sources of energy in galaxies, Through nuclear fusion, they convert mass into radiation, producing light and heat over billions of years. This energy regulates the temperature and ionization state of interstellar gas, influences the dynamics of galaxies, and provides the radiation backgrounds observed across the universe. The collective light of stars defines the visible appearance of galaxies and enables them to be detected across vast distances. Stars are also responsible for the creation of nearly all elements heavier than hydrogen and helium. Through fusion during their lifetimes and nuclear reactions during their deaths, stars manufacture the chemical elements required for solid matter, complex chemistry, and planetary systems. Every rocky planet, metal-rich object, and biologically essential element traces its origin to earlier generations of stars. The formation and evolution of galaxies are inseparable from the behavior of stars. Stars form from dense regions of interstellar gas, and through radiation, winds, and explosions, return energy and matter back to their surroundings. This feedback controls how efficiently new stars can form and shapes the internal structure of galaxies. Patterns of star formation determine whether galaxies grow steadily, experience bursts of activity, or gradually fade. Stars provide the conditions necessary for planetary systems to exist. Their gravity holds planets in stable orbits, while their energy output defines temperature ranges and environmental stability. Long-lived, stable stars allow planetary systems to persist for billions of years, creating opportunities for complex chemical evolution. The diversity of stars leads directly to the diversity of planetary environments observed throughout the galaxy. From a scientific perspective, stars are fundamental reference objects. Their measurable properties, such as brightness, spectra, and motion, allow astronomers to determine distances, ages, and masses across the universe. Stellar observations underpin the cosmic distance scale and provide the benchmarks needed to interpret observations of galaxies and the large-scale structure of the universe. Stars also act as historical records. Their compositions reflect the conditions of the interstellar material from which they formed, preserving information about earlier cosmic epochs. By studying stars of different ages and locations, astronomers reconstruct the timeline of chemical enrichment and trace how matter has been processed over billions of years. In terms of cosmic structure, stars define the visible skeleton of the universe. Galaxies are essentially vast collections of stars bound by gravity, and the distribution of stars outlines spiral arms, clusters, and galactic halos. Even dark matter studies rely on stellar motions to infer the presence and distribution of unseen mass. Stars influence the long-term evolution of the universe by converting matter into energy and by redistributing material through space. Although individual stars are small on cosmological scales, their cumulative effect over time drives irreversible changes in the universe's composition and energy balance. Stellar evolution is therefore a key component of cosmic evolution. For life as it exists on Earth, stars are indispensable. They provide the energy required to maintain stable climates, power chemical cycles, and sustain biological processes. The elements essential to biology are products of stellar activity, and the environments suitable for life arise only in the presence of stars with appropriate properties. In summary, stars matter because they transform a simple universe into a structured, evolving, and chemically diverse one. They generate energy, create elements, shape galaxies, enable planets, and provide the physical framework within which complexity can arise. Understanding stars is essential for understanding the universe itself, from its earliest moments to its far future.